recording. There we go, it's recorded. Okay, so the content for this week is implicit Runge-Kutta methods. So last week we looked at explicit Runge-Kutta methods and how we derive them. And so just a bit of, I'm aware I may be repeating myself a bit here, but it's always good to make sure we have this this down. Okay, so this is the general form of a Runge-Kutta method. Okay, you should be familiar with this by now. So it's a single step method, and we update our solution for the next step by using the values from the current step. So to update y, we add some weighted sum of what we call k values to yn. Okay, and the k values are calculated using whatever ODE function we're solving. So this f of ty here is our ODE function. The values of b, c, and a, they're the ones that determine what individual Runge-Kutta method we have, and it's more common to represent it as a butcher tableau. And I mentioned last week, but for some reason MATLAB doesn't allow me to have borders for this matrix. So here we have the a values in the top right region. We list the c values and we list the b values across. Okay, so that's sort of Runge-Kutta preliminaries. Now, with implicit Runge-Kutta methods, the order of accuracy is not necessarily determined. Well, it's not necessarily the same as the number of stages in a method. Okay, so we can use these order conditions I've got on the screen here. We can use these to determine what the order of our methods are. So if we're presented with a method, we don't know what order it is, we can use these order conditions to determine that. And the way it's done is you take your first order condition, which is the B condition, and you loop through J, so increasing values of J, and you check whether for your Runge-Kutta method, the left-hand side equals the right-hand side. And the highest value of J, which I've called K here, is the maximal order of your method. And you take your K and you halve it and round down, and then you check your C and D conditions for that value. If B is satisfied for K and C and D is satisfied for that half K rounded down, that means you've got a method of order K. All right, so let's have a look at an example. So here I've got a IRK method. Okay, so they're given by this butcher tableau. And to start with, we're going to look at the B condition. So the left-hand side, I'm going to expand out this summation here. So for j equals 1, 2, etc. And the right-hand side is just 1 over j. Okay, so when j is equal to 1, we have b1 times c1 to the power of j minus 1. So obviously when j is equal to 1, we've got c1 to the power 0. And when j is equal, j is equal to 1, so, and then we add to that b2 plus c2 to the power 0. Okay, so b1 is a half, b2 is a half, and obviously anything to the power 0 is 1. So half plus half is 1, and the right-hand side is 1 over 1, which is 1. So that's satisfied. Left-hand side equals right-hand side. Okay, for j equals 2, all we do is exactly the same. We just increment the power of the c values by 1. And so here we've got b1, which is still a half, and c1, which is 1/4, this is up here, plus half, which is b2, multiplied by c2, which is 3/4, which gives us 1/2. And 1 over 2 is obviously 1/2. So left-hand side equals right-hand side. Onto j equals 3. So again, we just increment the power of c by 1. Okay, so all we do is add increment the power of the bracketed number by 1. And you can see on the left-hand side, we have 5/16. And on the right-hand side, we have 1 over 3. So clearly, left-hand side does not equal to right-hand side. So this B condition is not satisfied for j equals 3. Okay, so the BK order condition is satisfied up to j equals 2, which is our K. Note there is an error in the printed notes. So I've since corrected that in the notes uploaded to Moodle. So this should say B2 rather than, I think it said B3 in the notes. So now we know what K is. Okay, So we halve k and round down. So k is 2. So we round down. Obviously, we get 1. And we need to check whether the C condition is satisfied for k is 1. So here we have two variables now. We have I and L for the CK condition. So L goes from 1 up to k. Now in this example, L is 1. So L is always 1. So we need to check the C condition for each stage. So remember, S is the number of stages of our method. Okay, so we're going to have two C conditions. So the C condition is when I is 1, we're going to have A11 times C1 to the power L minus 1, which is 0. So that's going to be 1. So it's going to be A11 plus A12. And that's going to be 1 over L, which is 1 times C1. So when L is 1, this is known as the row sum conditions. So the rows of A have got to equal C. Okay, so if I scroll down, you can see here, when L is 1 and I is 1, we have a left-hand side, which is A11 plus A12. So it's 1/4 plus 0. So obviously we've got a quarter. And the right-hand side is whatever C1 is. So that's going to be 1/4. When I is 2 and L is still 1, we have A221 plus A22, which obviously gives us 3/4. So a half plus a quarter gives us 3/4. And our C2 is 3/4. So left-hand side equals right-hand side. If we were looking for CK where K was greater than 1, okay, let's say K was 2, we'd have to loop through L is 1 and 2, and for each of those we'd have to check each stage. So if L was 2, we'd have 4 conditions, C conditions to check for. Okay, so onto the D conditions, we need to check for D1, and again we have L is just 1, but this time we've got J is 1 and 2 because we've got 2 stages. Okay, slightly more complicated order condition for D. Okay, so if I show you in the notes, in the example, so we have B1 times A11 plus B2 times A21. I can't quite get it on the same screen. Okay, so it's a half times a quarter. So B1 times A11 plus a half, which is B2 times a half, which is A21. So we get 3/8. On the right hand side, we'll have 1 over 1 B1 times 1 minus C1. So B1 is a half, C1 is a quarter, so it's half multiplied by 3/4, and that's giving you 3/8. Okay, so left hand side equals right hand side for the first column, and for the second column we substitute in the values again. Okay, and we can see that left hand side equals right hand side. So we can conclude that we have B2 is satisfied, C1 is satisfied, and D1 is also satisfied. So this means we have a second order IRK method. Okay, so that's how we determine the order of an IRK method. Now these order conditions, okay, if I scroll here, these are also used in the derivation of our IRK method. So we're going to return to those over the next few examples. Okay, is everything okay with that? Just put in the chat if you want me to just go over anything in a bit more detail. Okay, so on to deriving implicit run clutter methods. Now there are several different types, several methods. I'm going to look at a few of the common ones. And the first one we're going to look at is called Gauss-Legendre methods. And these are family of methods derived using Gauss-Legendre quadrature. So this is essentially we're using these what are called Legendre polynomials. These are solutions to the Legendre differential equation. Now, the thing to remember about Gauss-Legendre methods is an S-stage method has order 2s. Okay, so they're actually the maximum order for the number of stages is. So if you have a 2-stage method, it has order 4. Okay, and the Legendre polynomials can be written in this form. You'll see them in you can if you clicked on this link here, it'll take you to Wikipedia, and you might see it in a different form. What I've done is I've done a mapping to a form which we need to derive the IRK method. Okay, so what we have here is we have a summation. So Pn, n is the degree or order of our polynomial. So Pt is going to be a polynomial, and it's a sum from k equals 0 to n of n choose k, n plus k choose k, t minus 1 to the power k. So these may look like vectors, but they're actually the binomial coefficient. And what we do for Gauss-Legendre methods is the C coefficients are the roots of PST. So PS, S is the number of stages you have. Now the B values are chosen to satisfy the BK condition, and our A values are chosen to satisfy the C half K rounded down condition. So if we have a look at an example. Okay, so here we have the I want to derive a fourth order Gauss-Legendre method, so therefore we're going to have two stages. The C coefficients are chosen to satisfy, or the roots of P2T. So I'm going to use this equation here. So when k is 0, I have 2 choose 0, 2 choose 0, because n plus k is also 2, t minus 1 to the 0. And that's actually 1, because 2 choose 0 is 1. Okay. When k is 1, we have 2 choose 1 times 3 choose 1 times t minus 1. And when k is 2, we have 2 choose 2, 4 choose 2, t minus 1 squared. Okay, so if we evaluate that and simplify, we get 6t squared minus 6t plus 1. Okay, so using the easily solved using quadratic formula, we have C values of 1/2 plus or minus root 3 over 6. Okay, so we have our C values. We have a two-stage Runge-Kutta method, so we now got 6 unknowns to solve for. So we've got 4A values and 2B values. Now we need to, the B values need to satisfy the B4 condition, but because we've only got 2 stages, I only need the first 2 up to j equals 2. Is it j or is it I? I'm just going to remind myself. Okay. Yeah, j. So I use this BK order condition up to 2 because I've only got 2 B values. Okay. You could go further, but it'll be just an over-determined system. Okay, so the first 2 B order conditions, B1 plus B2 is equal to 1, and B1 C1 plus B2 C2 equal to half. Bear in mind, we already know what C1 and C2 are. So solving those will give me the B1 and B2. And then the first 4 C order conditions, so I need the order condition up to C2. I've got the 2 row sum conditions, and I've got A11 times C1 plus A12 times C2 equals a half C1 squared. Okay, so that's the first 4 order conditions for C. Okay, so now I've got 6 equations, I've got 6 unknowns, and we need to solve. Okay, so what I'm going to show you now is the use of the solve command in MATLAB. So this is quite useful. Obviously, we could solve this by hand. It's not too tricky, but you know, we got better things to do with our time. Okay, so first thing I'm always going to do is clear the memory, and then we're going to define the Legendre polynomial. Legendre polynomial, and I'm going to define it for a symbolic variable t. So sims, SYMS, t means t is now treated as a symbolic variable, and our second order Legendre polynomial was 6 times t squared minus 6 times t plus 1. Okay, so if I solve for the C values, okay, quite easily you could just say C equals solve, and in the brackets I'm going to say P2 equals 0. Okay, so I've defined my Legendre polynomial and called it P2. So if I solve for that, and if I click run or press F5, you can see it's solved, and it's given me that solution, which we already had because it's not too difficult. Okay, so what I'm going to do there is I'm going to store values, the C1 and C2 into variables C1 and C2. And now we're going to have to define the order conditions, which we've got up here. Okay, so these are 6 order conditions. So I'm going to define them in MATLAB. So first I have to actually define, specify that all our A and B values are symbolic variables. Okay, so notice there's no commas between these. Okay, if I tried to put a comma between them, it'll just come back with an error. So that's something, when you list them, don't put a comma between them. And let's get rid of that error. So what we do now is we list our, I'm going to call mine equation 1, equation 2, etc. It's quite simply, so I've called it equation 1 equals, and then I've got the left hand side with a double equals, and then the right hand side. Okay, so that's defined this equation, and it's called it equation 1. Equation 2 is similar, but we've got C1 and C2 values in there, and that's equal to a half. We've got the third equation, A11 plus A12 equals C1, which C1 I've already calculated that value there, so that's just going to be, I could have written half minus root 3 over 6, but it's easier just to keep them as variables. And the second row sum condition, and equation 5. What I'm going to do is, when we look at the further examples, I'm going to copy and paste all of this, so I don't have to keep typing it out, and you don't have to keep watching me type them out. So A21 times C1 plus A22 times C2 equals 1/2 times C2 squared. Now hopefully I've got those all correct. I'm going to double check them. Okay, we'll find out in a minute if I haven't got those correct. Okay, so we've got 6 order conditions. So I'm going to solve the order conditions using the MATLAB solver routine. So we list the variables I want to solve for in square brackets, B1 and B2, and using the solve command, I'm going to list all of the equations I'm solving. Okay, so I press F5. Okay, it's gone away and solved it. Okay, so you notice for A12 it's actually solved it, but it hasn't given it in a very nice form. So what we could do is, I'm going to do a bit of post-processing with these solutions. Okay, so a little bit of a trick when using MATLAB live scripts is, if you want things outputted all at once, is just put them in a loop, for loop with one iteration. So I'm going to say A was A11, and then I'm going to simplify A12 because it gave it in a bit of a complicated form. I think A21 was okay, and A22 is okay. B was B1 and B2, and I'd already calculated C. Okay, so you can see it's simplified that A12. If I didn't have that, okay, for some reason it didn't automatically simplify it, but that's no big deal because we can use MATLAB simplify command. Okay, so there we have elements of our butcher tableau. We have our A matrix, our B values, and our C values. So this is a 4th order Gauss-Legendre implicit Runge-Kutta method. Now what I'm going to do here is I'm going to reuse some of this. I'm just going to copy it for some later examples. Okay, there's no point typing them all out again. We can use a lot of what we've done before. Okay, so that's the Gauss-Legendre method. Other types of methods, I'm going to go through them. Okay, so Radal methods. This is the there is a problem with Gauss-Legendre methods. They're very accurate. So an S-stage method gives you an order 2S method. but they do compromise in the stability properties, and I keep mentioning, but we'll be doing stabilities next week in week 3. Now, Radal methods, what they do is they compromise on accuracy in order to get better stability. So first thing to know about Radal methods is an S-stage method has order 2s minus 1 and is something what we call astable, and we'll be covering astable next week. Now, there are 2 types. There's type 1 and type 2, and their derivation. Okay, the type 1, what we do is we let C1 be equal to 0, and the other C coefficients are the roots of PS plus PS minus 1. So remember, S is a number of stages. Okay. Oh, sorry. Yeah, S is a number of stages. And to calculate the B coefficients, we use the B order condition, and to calculate the A coefficients, we use the C order condition, the same as what we did before. The second type, okay, the C coefficients are roots of PS minus 1. So first type is we add them together. The second type we subtract them. And the B and A coefficients are calculated from the B and C order conditions respectively. Okay, so this is quite similar to the Gauss-Legendre derivation. So let's have a look at deriving a third order Radal type 1 method. Okay, so we want third order, so k equals to 3, and k is 2s minus 1, so therefore s must be equal to 2. The values of c are the roots of p2 plus p1, which this is p2, which we used in the previous example on the Gauss-Legendre method, and p1 is simply 2t minus 1, which gives us 6t squared minus 4t. Quite easy to calculate the root of that, which is 2/3. Okay, so the values of B and A need to satisfy the order conditions from B and C. So essentially the same as in the previous example. So because it's the same as the previous example, I'm going to paste in. Okay, so I just pasted in what I copied from example 3.2. I'm going to have to change something, but the only thing I'm going to have to change is this thing down here, where I'm going to have to add the this is the, I just put some brackets around. So this first one was my I'm going to call it P instead, because it's not, strictly speaking, it's not P2. Actually, I'm going to make slight changes just to be accurate. So that was my P2 from before, and I'm going to call it P1. Okay, just to be a bit more accurate. Okay, so here we need to solve P2 plus P1. Okay, so that'll give us our values of C1 and C2. Okay, and then we need to calculate the order conditions. This is exactly the same as it was before. Okay, so we've got 2 stages, so we need 2 order conditions for B1 and B2. Okay, so that's these 2. And we have 4 order conditions for the remaining A values. So actually it's very similar to the Gauss-Legendre method, except for our C values are calculated by solving P2 plus P1. Okay, so what I'm going to do is run that, see if it works. There we go. Right. Okay, so there we have the type 1A order condition. Okay, so that's your butcher tableau, or your elements of your butcher tableau. We probably didn't need that simplify in there. Let's just check. Yep, that worked out okay. So you can see, but using MATLAB solve routine, it's quite, it takes all the legwork out of it, but you've still got to understand, and in your assignment, you've still got to show where all these order conditions come from. Okay, in your assignment, I think it's a 5th order Radal type 2 method. So you'd be using this here. Okay. Okay, so another form of IRK methods called the Dirk method, or diagonally implicit Runge-Kutta methods, and this is a class of implicit Runge-Kutta methods where the A matrix is lower triangular plus it has some values on the main diagonal. Okay, so if this was lower triangular and all these main diagonal elements were 0, we'd have an explicit method. Okay, but here, because we have some non-zero main diagonal elements, we have an implicit method. Okay, well, this gives us an advantage over other implicit methods in that when we calculate the first order condition, sorry, not order condition, when we calculate the first stage, we can calculate the first stage without having to know the values of all the other stages. And then when we calculate the second stage, we already know what the value of the first stage is, and we don't need the values of the subsequent stages, etc. So it can be calculated sequentially. So to derive the DIRT method, okay, so I've chosen to satisfy, so all the A's, B's and C's are chosen to satisfy the B and C condition along with this. Okay, so this is an additional condition. So before, with the Radel and the Gauss-Legendre method, we knew what our C values were because we were solving or finding the roots of the Legendre polynomial. But for DIRT methods, we don't have that luxury. But what we do have is we have fewer A values to solve for because all of these will be 0. Okay, so let's have a look at an example of a two-stage third order DIRT method. Okay, so we've got 2 stages. Okay, so we've got 2 stages, and our butcher tableau would have 2 C values. Okay, it would have 2 B values and 3 A values because the A22 would be 0. Sorry, A12 would be 0. So we need to solve because we don't know what C values are. We need 3 order conditions borrowed from the BK order condition. So we have to go up to B1C1 squared. Okay. We have the row sum conditions. So remember A11 plus A12 is equal to C1, but of course A12 is equal to 0. And the last condition we have is this. So what I'm going to do is actually switch windows a sec and show you where this comes in. Okay, so we're just going to quickly switch windows. Okay, can you all see like a dark green background? Is that what you can see? Are you still there? Oh yeah. So sometimes I think it could be nobody there, but yeah. So you could all see that. Okay, so what we're going to do is we have this order condition. Okay, so that was our additional order condition for the DIRT method, and our example is we had a butcher tableau. I've got 2 stages. I had A11, A21, and A22. So that's what I mean. So we have 7 to solve for. Okay, so we need 7 order conditions. So this one here. Okay, so by the way, the B and C vectors, they're always assumed to be column vectors. So B transpose is actually B1, B2. We have our A matrix. And we have our C column vector, C1, C2. Okay, so if we calculate what this is, or do the matrix multiplication, we've got A11, C1 plus A12, C2. And we'll have A21, C1 plus A22, C2. And that is, of course, equal to B1 times the first row, and plus A12, C2 plus B2 times the second row. Well, of course, for this one, okay, this bit is 0, so we don't, A12 is equal to 0, so it just cancels out, and so our order condition is B1, A11, C1 plus B2 A21 C1 plus A22 C2. Yeah, so that's our kind of seventh order condition. So we needed that because we needed that's what you need for a Dirk method. So remember, that's an additional order condition just for the Dirk method. Okay, so that's just in case you're wondering where I got my last order condition from in that one. Okay, is that the right one? Just checking. Going back to, yeah. Okay, so that's where that last order condition came from. Right, so here we have a system of 6 equations, 7 unknown. So we need to solve for these. Okay, if I can copy in what I've done before to a certain extent. Okay, so I'm not going to have my Legendre polynomial. Okay, so I need to solve for add C1 and C2 to my solution. So my first two are okay, equation 1 and equation 2. My third equation, I need another one of the B condition, but this time C1 and C2 is squared. And that's 1 over 3. Okay, my fourth order condition is the row sum, but remember A12 is 0, so I'm just going to delete that. And that one's the same. Okay, I'm going to have 6 in total, and then I got so 1, 2, 3, 4, 5, 6, 7. So I'm solving for 7. So I'm solving for 6. So the last order condition was that one which we just determined. Okay, so we have 6 order conditions. We have 7 unknowns. So one of our values we're going to have to select, like we did with the explicit Runge-Kutta method. So what I'm going to say is let's C1 be equal to 1/4. Okay, I've specifically chosen C1 to be equal to 1/4 because it means we get some nice values elsewhere. If you were to choose other values of C1, you might get some horrible square roots appearing. Okay, so then we need to solve our order conditions. So we have B1, B2, and we also have C2, which is unknown. So we know what C1 is. Okay, so we're going to solve for that. Okay, so let's see what happens when I attempt to solve for that. Okay, I've got an error here. So 2, 3. Okay, let's see what this error is. And oh yeah, I'm trying to solve for A12, which is 0. Anybody else spot that? Okay, so just undo what I had A12 as being a solution, but as you can see, it's not present. I had it as an output. That's what I wanted to solve for, but it's not present in any of my equations because it's just 0. So if I delete that and run again, okay, yeah, you can see. Okay, so it's given an A12. What I can actually do is also actually specify. We know that A12 is going to be 0 because we've got a Dirk method. Okay, or I can just say that's 0 there. It doesn't really matter. Just trying to tidy things up. There we go. Oh yeah. So I should also have listed the C1s. Okay, so that's the Dirk method, or a Dirk method for this, for a third order Dirk method, what we had here. Yeah. Okay, so the only difference is we have this additional order condition there. Okay. Dirk methods are useful, but there is a variation on the Dirk method which makes things a little bit easier and have better stability properties, and that's called singly diagonally implicit Runge-Kutta methods, or known as Esk-Dirk methods. So what it is a variation on the Dirk method, but what we have is our main diagonal elements all have the same value. And of course, by the first row sum condition, our A11 has got to be equal to C1, So that means all of our main diagonal elements on A are equal to C1. Okay, now the derivation is the same as before. Okay, but here we have example 3.5. So I'm going to do the same as before. So I'm actually going to borrow my code from here, and I'm going to derive an S-dirt method, a two-stage third-order S-dirt method. Okay, so the first three conditions are the same as the dirt method. Okay, but what you got to remember is I'll include this condition here, A11. But what we're going to remember is that A22 is also equal to C1. Okay, so where I see A22, I'm going to replace it with C1. Okay, just those two places, and I'm not solving for A22 anymore, so I don't need it. Okay. Right, so just checking I've got everything correct. So I need all those ordering conditions. So I'm not solving for A11 because I know it's C1, and I'm not solving for A22 because I know it's C2. So I've got, in this case, I've got 4 unknowns. Okay, sorry, I should have 5 unknowns. C1, don't actually know what that is. So here I don't need to specify what C1 is, because it's going to solve for it. So if I click run, okay, didn't know what A22 was. That's because it should be equal to C1. Just carry that. So that there. So A11 and A22 are both equal to C1. Okay, so I've got a bit of a problem here. I think I might have an overdetermined system. So I'm just going to make a couple of changes. So I've got 5 unknowns, and I only need 5 equations to solve for that. And just double checking. Yeah, so A11 is undefined. Okay, that should be equal to C1. Okay, so I don't need an A11. And I don't need an A12 because that's 0. Try again. Yeah, doesn't. A11 should be C1. Okay. You never get these first time. Oh, right. Okay. Right. In good old-fashioned Blue Peter, I'm going to bring in one which I've done earlier. I don't know whether anyone spotted an error there, but rather than me messing about, I'm going to bring in one which I've done earlier, and I'm going to run that. So I don't really know what the difference was between that earlier one and this one. Okay, I must have made a minor mistake somewhere. Okay, so after we've sort of flapped around with that a bit, okay, so for an S-dirt method, as you can see here, I've got a solution. So I've got an A, that's my S-dirt. Notice all the values on the main diagonal of A are the same, and that's equal to C1. B is a half and a half, and C is this. We've actually got 2 solutions for this one. So if we reverse the signs in A and B, we've got an equivalent method as well. So we actually have 2 S-dirt methods found by alternating the sign of the root 3 sign. Okay, that's as far as I'm going to go in terms of deriving implicit Runge-Kutta methods. There's a lot more out there, but they're all derived in a fairly similar manner using those order conditions. Now, just notice the time, it's 10 to 1, so I think we'll have a 10-minute break there, and we'll resume again at 1 o'clock. So before we go on a break, are there any questions about what we've just gone through for the last sort of 50 or so minutes? You still there? Or have you all nodded off? Good. We've got some questions. Good. So the question from Sarah here is, for the coursework, any working out we do on paper, do you want to see that too, or do you just want to type it all up? Yeah, I want you to show full working. So, for example, when we looked at the Gauss-Legendre roots of the Gauss-Legendre method, the Legendre polynomials. I want to see how that's done. If you do use MATLAB solve routine, I want you to show, or on your PDF submission, I want you to show what commands you've used. The reason for this is, if let's say you don't get it quite right, I can award part marks if I know where you've gone wrong. But if you don't show your working, I can't award you any part marks. Okay. Yeah. Okay. No more questions. I'll still be here over the 10 minutes, but you can go and grab a drink or have a break. Stella, are you allowed to do some work on paper? Rough work you can do on paper, but we want to see it. We want to see it typed up. You're all final years now, so we're going to try and sort of encourage a bit of sort of professionalism in the presentation of your work. So you can do that in Word or LaTeX if you've ever used LaTeX before, but we want to see it typed up. Okie dokie. All right then, I'll see you guys in about 7 minutes.